For centuries, finance operations revolved around a single, highly manual task: recording static history. Clerks painstakingly wrote every transaction in centralized ledgers. That analog model fractures under the weight of a modern enterprise. Relying on human hands to process thousands of global transactions means the workflow inherently slows down. It creates bottlenecks, introduces localized vulnerabilities to fraud, and fails to scale. To survive, organizations must abandon manual processes entirely. The static ledger dissolves into a fluid digital infrastructure, connecting every node in real time. This transition requires business process reengineering. You cannot simply digitize old paper habits and call it innovation. Reengineering means completely disregarding current hierarchies and reporting structures to build a streamlined, optimized workflow from scratch. We are going to construct a theoretical 4-layer modern finance stack. And to ensure this massive transition doesn't accidentally destroy current operations, we will build it using a proven methodology called the Systems Development Lifecycle, or SDLC. Today's finance professional architects the autonomous systems that process data, moving beyond the simple recording of history. Before a company buys a single piece of software or writes a line of code, it has to manage the extreme operational risk of transitioning its technology. This requires a foundational blueprint. The Systems Development Lifecycle provides exactly that: a disciplined 7-phase framework for developing large application systems. Looking at the top of the cycle, Phase 1 focuses on initiation, feasibility, and planning. This is anchored by an organizational needs assessment. The assessment forces an organization to study exactly what its current systems can handle and clearly define the exact gap between that capacity and the company's projected future growth. Once the gap is identified, the cycle moves to Phase 2, requirements analysis. Here, IT and finance must formally agree on exactly which business functions the new system will affect, what technology it requires, and what economic resources must be committed. Skipping these initial phases to rush headfirst into a new technology purchase does not accelerate innovation. It simply automates a company's existing chaos, only faster. With the blueprint established, we can build the first tier of our enterprise architecture. The base layer is cloud computing. Rather than maintaining physical, on-premise servers in a backroom, cloud computing provides on-demand access to shared computing power and storage over the internet. This layer can deliver virtualized computing resources through infrastructure as a service, provide application development tools via platform as a service, or offer web-based software subscriptions known as software as a service. The financial advantage of this model is immense. Companies shift away from heavy, upfront capital investments in depreciating hardware, moving instead toward a highly flexible, pay-as-you-go operating expense model. However, this layer introduces a new risk vector. By relying on third-party providers, the organization inherits those providers' security vulnerabilities and faces the threat of external service disruptions. The cloud provides a highly scalable foundation, but it forces finance teams to manage vendor risk with the exact same rigor they use to manage their own internal ledgers. Sitting directly on top of the cloud environment is the execution layer. This is where robotic process automation, or RPA, drops in. RPA is software designed to acquire knowledge and mimic human keystrokes. It uses graphical interfaces to process data for highly repetitive, rules-based tasks. The immediate operational payoffs are clear. Robots can work 24 hours a day, 7 days a week without breaks. And once programmed correctly, RPA entirely eliminates human data entry errors. But RPA is a flawless executor of the predictable. Because it relies on rigid logic, it is blind to context. The moment an RPA bot encounters ambiguity or an exception that isn't explicitly written in its instructions, the process breaks. To solve the rigidity of basic automation, we add the AI logic layer. Traditional software relies on strict if and then conditions, with only 2 possible outcomes. Artificial intelligence, however, attempts to replicate human reasoning. It uses intuition and experience to handle high degrees of complexity. Consider a corporate audit. A traditional human auditor can only manually review a tiny, randomized sample of a company's total disbursement documents to check for fraud. AI changes this dynamic. Instead of sampling, the system ingests 100% of vendor invoices and employee expense reports simultaneously. Over time, the AI learns what a normal transaction looks like for the business. It automatically evaluates thousands of variables to flag subtle anomalies and non-compliant disbursements that a human scanning a small sample would completely miss. RPA provides the muscle to move data. AI provides the judgment, transforming the entire system from a passive record keeper into an active, self-correcting fraud prevention agent. We have a sophisticated architecture on paper, but transitioning a live, functioning business from its legacy system to this new 3-layer stack is the single most dangerous phase of the transformation. To navigate this bottleneck, we look back to the SDLC blueprint, specifically Phase 6, acceptance, installation, and implementation. One approach is the direct cutover conversion strategy. The old legacy system is entirely shut down, and the new stack instantly takes over live operations. This is the fastest and least expensive method to implement. However, it carries the highest risk of catastrophic, company-wide failure if the new system malfunctions. The alternative is parallel operation, where both the old and new systems run simultaneously at full capacity. This redundancy makes it the safest route, but it is by far the most expensive and time-consuming option. Organizations can also choose middle ground approaches, like pilot or phased conversions, which implement the new system one department or one function at a time to isolate risk. You can design the most advanced technology stack in the world, but it is useless if the conversion strategy you choose destroys the company's daily operations during implementation. The architecture's final layer provides a foundation of decentralized consensus. This layer operates on blockchain, a digital ledger that records transactions and proves ownership without relying on a single central database. The security mechanics are based on cryptographic consensus. Multiple independent nodes in the network must agree to add a new block of data. To falsify a record, a bad actor would have to successfully hack and alter over 50% of the entire global network simultaneously. Built directly on top of this ledger is a powerful operational tool known as a smart contract. Smart contracts are highly deterministic, auto-executing code. They automatically release funds the exact moment specific conditions are met. This effectively eliminates the need for expensive, trusted intermediaries like lawyers or escrow agents to manually enforce an agreement. This technology shifts corporate trust away from easily manipulated internal spreadsheets, moving it onto a mathematically guaranteed, publicly verifiable consensus. Let's watch a digital vendor invoice flow through this architecture. It hits the cloud layer for secure hosting. Robotic process automation perfectly routes it to the ledger. AI simultaneously scans against historical records, verifying compliance. Finally, a smart contract seamlessly executes payment on the blockchain. But enterprise systems are never truly set it and forget it. We return to the final node of the SDLC. Phase 7 mandates continuous operations and maintenance. After the system has run for a substantial period, analysts must conduct a post-audit evaluation to ensure the technology actually adapts to the company's shifting business goals. Achieving a zero-fraud, highly scalable autonomous enterprise requires a continuous, disciplined architectural integration of these technologies, rather than a single software purchase.